not here, but I do a lot of. At one point, a couple of years ago, we were like a bunch of us would do it. We're gonna get like T-shirts. How you doing? Good. The weather is just like in Boston, no humidity. It's good. Yeah.
Okay, we'll get started as people are wandering in. So, welcome to the Usable Formal Methods Research Group meeting today. My name is Stephen Farrell. My co-chair Jonathan is gigantically on screen and is remote today. Did you want to say anything to Jonathan, or hello, or? Okay.
Hi, folks.
Fair enough. So this is a research group, part of the IETF. So the IETF follows the same IPR rules as the IETF. We're going to be recorded. I guess you've seen most of this before. Be nice and be respectful and so on. I'm sure we hopefully will all be. And just for in case somebody who's less familiar with the IETF, the IETF doesn't produce standards, but we do kind of look at longer term research topics, including making formal methods usable, which kind of seems long term. And that's our administrivia. Our agenda today is quite short, so we're not short of time. So if people want to discuss or chat, that should be entirely fine. We first have Osama is going to talk about a tested TLS. And then Tahina is going to give us a talk on EverParse. Does anybody want to bash the agenda? Don't see anybody who does. So we have 2 hours allocated. I'm not sure we'll use 2 hours, but we do have time. So, and with that, we'll go over to Osama. And I presume you want the clicker, Osama, yeah? You have clicking powers. Yeah, I think you don't point it over that way.
Okay.
Okay.
Okay, so welcome everyone, and thank you, Chairs, for this opportunity to talk about tested TLS again. We talked about it in a couple of meetings ago, and we are going to present the update to this tested TLS. And I want to thank, first of all, Confidential Computing Consortium, GenXT, and Teleport, who sponsored me to be here. And also, I want to acknowledge Arto, Hannes, Thomas, Simon, Ned, Mariam, Thomas, Yaron, Jonet, and Jan Mary, who have actually contributed to a number of papers which are under submission or accepted already.
So that list is getting longer.
Yes, as tested TLS is getting traction, so it's very important for confidential computing, and people are joining us. Thanks a lot for to all of them who have contributed. And other than those people who are here, also we want to thank UFMRG who have given us feedback and otherwise. So as I have planned today, I want to just remind a little bit about what the problem was, what the background of the whole problem space is, and then a little bit about the formal modeling, what we did, what we have currently, what we are looking for in the next steps, and the problems we found, and on the third point, like the potential solutions that we have proposed, and then finally a realistic threat model for confidential computing, which is itself debatable between the Confidential Computing Consortium and academia and all the things, as well as the vendors. Every vendor would like to project its own solution and like to have the security properties which favor their solution rather than other solutions and so on. So it's really an ongoing challenge for us to agree upon a set of properties that really everyone is happy with, and from a scientific perspective, which makes sense, that is some guarantees that we get out of that. So finally, I will then conclude. The context for this goes back to the draft. IETF 121 presentation was made on this draft for Sati TLS attestation. The idea was to introduce attestation within the TLS protocol, and the proposal was to do it within the handshake itself, such that one can, when the protocol is finished, that is the parties establish a connection, you already have that evidence verified. And if that something is not as expected, that is, for instance, the hash value does not match, then don't even establish that specific connection. They asked for adoption in the TLS working group, and for TLS working group, as many of you may know, there are FAT requirements that a formal analysis is required. This was changing even the key schedule for that, and that's why formal analysis was definitely one of the things that was required to be done. We started already then, back then, and the formal analysis under the confidential computing threat model in ProVerif as the verifying tool, we found that it breaks server authentication straight away. I will show you it. Maybe doesn't even need ProVerif for that, because it's actually understanding of how the keys work and so on. And I will explain you in one of the slides. So this is meant to be just a context.
Just to check, two things I forgot to ask. Do you want people to jump in and ask questions?
Sure, yeah, everyone is welcome.
And second, I don't know if people are familiar with the FAT, for the TLS FAT thing. How many people kind of know what that is? Yeah, so maybe you might want to explain that a little. Yeah.
Sure. So the FAT process is that, at least in my understanding, that when a proposal is made to a working group, namely the TLS working group, a new draft is floated and they ask for adoption. The process will go through a formal method team of experts, which is, I believe, 6 or 7 experts at this time.
But not everything has to go there, but
yeah,
essentially anything that touches the key schedule.
Yeah. So non-trivial extensions of the TLS protocol will go to them to evaluate whether it's does require a formal analysis or not, or what the next steps should be from a formal perspective, if it is required. Some kind of intuition, I think, on what kind of properties might be interesting for that specific draft to be evaluated. So this is the core idea, that formal analysis is now tightly integrated into a non-trivial extension of the TLS protocol. And the whole idea is that to maintain the cryptographic properties of the TLS protocol itself, that any proposed extension does not, let's say, reduce the value of the formal method of guarantees that we already have. Is that kind of a good summary? Okay, good. And please feel free to come to the mic if you have any questions. So the challenge here was there is a lot of terminology held in remote attestation, which is the RATS working group of the IETF. And what the members claim there is that, okay, so we want to be vague, and for formal methods, as most of you might know, so we want to be more precise. So there is natural conflict there going on, and they keep introducing new terminology without saying what exactly that is and what exists, what is the difference from the existing thing to the new defined things. They keep inventing their own terminology without looking at the literature or the research papers and so on. So there is a lot of terminology gap which is required to be mapped, unfortunately. So what I do now is to give a very, very abstracted view in this. And in that, it means there are 3 parties in remote attestation procedures. I will reduce it to 2, meaning that the verifier plus relying party, I will take them as one specific entity. And the other one would be the entity which I want to establish trust with. I want to check what that entity is. That would be the attester. So that would be the simplifying context. And in this slide, you see exactly that, which is on the left side, the standard TLS PKI infrastructure, which is namely the certification authority is the root of trust or the trust anchor. And the server and the client are the 2 roles in the TLS protocol. Before they start the protocol, server sends over a certification signing request. It gets back a certificate, and the certification authority by some means configures the public key into the client, and then they run the TLS protocol to establish the secure channel based on that specific certificate. And the long-term key is represented by LTK, and the private part is the priv LTK, which the server is authenticated with. Really analogous to that is the RATS perspective, which is the remote attestation on the right side. What changes here is hardware manufacturer is now the trust anchor. That means that it provisions some new key, which is called as the attestation key, into the attester, and attester itself is also distinguished by an ephemeral key, which is shown as the EK. And then there is the public part of the attestation key, step number 2, shown here by the hardware manufacturer. Somehow on their website or somewhere they publish it such that the verifying and relying party can get that and check the signatures, which would be done by the attester with the private part. So it's simply a signature in very, very simple abstract forms, nothing much complicated. You send over a challenge and then you get back a signature, you verify signature, you get some trust, and the trust comes from the public key coming from the hardware manufacturer, and that's what you trust. Jonathan.
Sorry, just the evidence doesn't require knowledge of the private EK?
Evidence does require that
So
because
your slide, it says evidence equals sign using the private AK,
sure.
and then you include the public EK, but you don't rely on the private EK for this evidence?
There is so it's a very abstracted view. What will actually happen would be like that you will have a hash of the private key priv ek into that, and then you will, just like TLS protocol, you will provide proof of possession of priv ek by signing the transcript that I will explain in one of the protocol designs. Like, this is at a very high level view, but in protocol design, you could use that private priv ek to sign to provide the proof of possession that I possess actually this key and it's not borrowed maybe or relayed from someone else. Okay. Does that answer your question?
Yeah, I mean, so basically there's more to evidence than is written on your slide.
Yes, sure. So yeah, that's then a whole protocol. That's just a view to compare. Just like in TLS protocol, certificate is one part of the protocol itself. And there are a lot of things going on, like certificate verify, you provide proof of possession, and then finish message to get that we have the same transcript. Similar to this, one can design a protocol for evidence, which is what they also did, the authors. And that provides the proof of possession of priv ek, similar to that. And yeah, so that will be in one of the slides in the protocol design. Okay, so really analogous to identity in the PKI infrastructure, that is the subject alternative name. We have M here representing the measurements, that is what is the hash of the code which is running on top of that hardware. So very, very abstracted view, just to set the scene to that it is quite analogous to what we have in the PKI infrastructure with TLS, and one can design it similar to what is there. So formal modeling part, what we need here is the description of first the cryptographic keys, and this slide is really, really important because there is a lot of misconception on the number of keys and specifically which key does which role, and that's what I want to emphasize here. There is one attestation key as was represented by AK on the last slide, which the hardware manufacturer actually provides. In addition to that, there are the TLS identity keys, which are number one, the long-term key, which we typically have in the normal TLS, like the CA certified key, which was the left side of the last slide. And we have on the right side of the last slide was the ephemeral key EK, and that is self-issued. There is no authority which the attester has. So it is self-issued by the attester itself to provide that I possess this key. So that's really important because when we are designing protocol, it has to be mentioned like which key are we talking about, and there was a bit of an ambiguity about which key is being used and so on. And this kind of represents the main keys which are important from cryptographic perspective. Yes, please.
So just for clarity, so is the LTK just a normal TLS server
Sure.
private key?
Right. Yeah.
And
Just like this one, like this TLS protocol, it's very similar to what is on the left side of this picture, like LTK for the server. And if we assume, let's say server is the attester, that would be the priv EK would be the other key.
Okay, and on the latest slides, so AK and TIK are new things in attested TLS?
I would say only the EK is the new, yeah, AK and EK are the new things. TIK is just a terminology that you have used to kind of distinguish between attestation key and TLS key. So LTK is the normal one which we have in the C assigned and normal TLS. So the one new key is the one provided by the manufacturer, attestation key. And the EK is to distinguish. So on top of the same hardware, for example, this machine, one could have multiple VMs, right? And
Sure.
And to distinguish the multiple VMs running on top of the same machine, we need to distinguish them.
Okay.
So you can think of each EK representing each VM and each LTK representing that specific machine on top of which these VMs are running.
Okay, sorry to be slow and confused. So LTK is the normal TLS server private key.
Sure.
And TIK is a new thing that's not part of normal TLS?
Let me rephrase it a bit differently. Let's say, so the key, the new thing is EK, ephemeral key.
I understand AK and EK are new, yeah?
Yeah,
I'm not
yeah.
confused about TIK.
Okay, so the TIK is basically just say, let's say, TIK can be LTK or EK. That's what I want to represent in this.
Okay, so it's not an actual new key.
No, it's not new key.
It's a concept.
It's a concept that to represent both keys. Sorry for the confusion.
I understand that, thank you.
So the three keys are AK, LTK, and EK.
Right.
And just to distinguish or put them in one category, TLS identity key is just a concept that it's.
Great, thank you. Gotcha.
Yeah, welcome.
Jonathan has something as well.
Yeah, Jonathan.
Yeah. So I'm just trying to work out who knows these keys. So is the attestation key shared by lots of hardware that's all manufactured by the same manufacturer?
Right. So Intel had one scheme where exactly that was the case. They had multiple SGX machines which shared the same key. So the kind of the group identity concept, enhanced privacy identification, EPID. But early this year, they have announced not even announced, I mean, it's finished. So it has reached its end of life. So that solution no longer exists, which means that now the current solutions only have one attestation key per machine.
Okay, so the attestation key is unique to each machine. Every machine has a different attestation key.
Yes, ideally. I mean, manufacturers could do it multiple per machine, but ideally, like this is.
It's not about how many keys are in the machine. I care about how many people know the private key to attestation key. And that's lots of different pieces of hardware.
If I understand you correctly, you are saying whether this is one-to-one mapping between AK and physical machine. Is this correct?
Yeah, sure.
Yeah. So I talked to ARM guys yesterday, and that was the discussion. And they said our specific, and for ARM, it's a bit difficult, different. I mean, sorry, different because they manufacture the IPs, and other manufacturers will then manufacture the device. And they told me that their specifications do not limit the manufacturers to have it really unique per device. So it's still possible that, let's say, Fujitsu building on top of ARM specifications IP, they could inject the same attestation key into two different machines, and they would still satisfy the ARM specifications.
Okay, so the attestation key could be on multiple machines, but it tells you who the manufacturer is. The LTK is unique to each machine?
Yes.
And then the EK, is that unique to each session? So if I attest, I've got one VM, it does an attestation, and then it does another attestation in the future, does it use the same EK or a different EK?
Can you please repeat? I didn't follow that.
So I want to know, does ephemeral key only ever get used in one handshake or in one protocol run, or is ephemeral key used as long as it's the same VM?
EK really depends on the use case. Not on the use case, on the protocol design, which means that there is a protocol which I will explain, like the internet draft used it for each session. It was uniquely generated ephemerally within the TEE. And whereas Intel does it differently, that they use it for all sessions, the same ephemeral key for all sessions of the server. So it really depends on the.
It's not always ephemeral. Sometimes it's a long-term key.
Yeah, in terms of in that sense, yes.
Because obviously I'm just trying to understand what the security properties of these are. And
Right.
basically, attestation key effectively tells you nothing because lots of different people know it. The long-term key is unique, so that's useful. And then ephemeral key is just another long-term key.
Not necessarily always, but it could. It's important. EK is important because it is.
Like you don't get if you can't rely on a property, it's not a security property. So, like yes, sometimes it might be unique, but in general, it's not unique.
So if I understand correctly, the uniqueness of EK depends on whether it's your pre-handshake or post-handshake scheme.
Yeah.
So you're trying to fixate. You're trying to fix that in your protocol. Is that correct?
It would depend on the protocol category that you have. Like in pre, it would be kind of long-term, as he said. It would be same across all sessions.
Yeah.
But in, let's say, in intra, I could also design a wrong protocol in which I could reuse it. I mean, it's really on the protocol design. The terminology ephemeral actually comes from confidential computing, where they say, just to distinguish it from long-term key, it's not about the lifetime of the key. It could be really a long session ongoing for telecom, for instance. Thiru has a use case there. But the point really is that this is distinguishing a virtual machine or an enclave rather than the device itself.
Gotcha. Okay.
And there could be multiple VMs on the same machine. So that is what it distinguishes. Like on the cloud, it could be so many VMs for different, let's say, customers running on the same physical machine.
Okay. And then, Jonathan, I think LTK also could be shared across machines because somebody might just clone the same TLS server cert, right? So I think all of these things may or may not be unique per something. And then as you define your protocol, you try and constrain that down, I guess.
Right. Yeah.
Okay.
Okay.
Thanks.
Okay. So with these set of keys, a very minimalistic set of keys, what we do now is to define the threat model of what it is all about, like standard TLS threat model, which is the weak Diffie-Hellman, weak hashes, and bad elements, as is used in the standard TLS verification. On top of that, we have the long-term key, which may be leaked for device specific key. Attestation key, which we have an additional key compared to the standard TLS, may also be leaked, like attacks like Foreshadow, which have practically shown it. And then on top of these threat model, I distinguish the assumptions, meaning that from my understanding, at least they are complementary to the protocol design, which means that I can't really provide a good set of guarantees on that. That is something coming from the system architecture itself to be ensured by the system itself, which means that the generation of claims was happening correctly. There were no weaknesses in that. If I was provided somehow by wrong claims, so of course I cannot really detect that unless there are some other system level mechanisms. And the verifying relying party, meaning the other peer which is checking the state of this machine, has to be provisioned with the correct reference values. Reference value term coming from RFC 9334. Roughly speaking, it means that hash of the code. Yes, please.
Sorry, what are claims?
So claims are the attester generates its claims for some some trustworthiness claims, such as I claim that, let's say, this piece of code is running on top of the machine that I have, and that it has a specific software version number.
So basically the things you want to attest to.
Yes.
Good. Yeah.
Right. Attestation claims. Yeah. And then reference values are the reference values for these claims, meaning that in claims, I provide what hash value is the piece of code running on the attester, and correspondingly what hash value I actually wanted to run on that is the reference value. And if they both match, then is my piece of code which is running is the one I expected to run. Then finally, there are time of check to time of use attacks, meaning that I can check at a specific point in time, and I have no guarantees whatsoever would be afterwards, meaning that unless I have some guarantees from the hardware that nothing changes, everything is pretty much static. If I don't have that guarantee, then I cannot provide any guarantee on what will run or what will be happening afterwards. So that's something which is, I believe, very, very hard to provide at the protocol level and has to come somehow from the system architecture level. And that's why I call it assumptions rather than putting it in the threat model itself, like what the properties itself will contain, meaning that if I sign right now, I cannot provide any guarantee afterwards of that. Time of check, meaning the signing of the claims, time of use, meaning that when they were appraised in RFC 9334 terminology, or in simple words, like when it was checked. Okay, with that, the second thing is the informal security goals. What do we want to achieve with this combination of attestation and TLS? Of course, we want to preserve the standard TLS properties, in particular server authentication, assuming server as the attester. And then from the remote attestation side, as I said, things are pretty much vague. What we came up was that the claims, the attestation claims that the attester is making, they are not modified on conveyance from the attester to the verifying relying party, meaning that if they are changed, they are detectable changes, and they are fresh, meaning that if I ask for a state of that machine, they are freshly generated and not already stale. And the third one is a subtle difference from freshness, which is we have not yet formalized, meaning that attestation credential refresh at any point in time after the session has been established. I could, this property says that, or this goal is basically that allows me to check the state of the machine after the establishment of the channel. That if something is changing, I can still query, and whenever I query the attester, it can still provide me the latest state of that specific machine. So the difference here is freshness only for the first time, and then refresh that I can repeatedly do it for post-handshake posture assessment. Right, the two things we want to preserve their properties, and in addition to that, the composition of both has to be preserved, meaning that I should really be ensured that the machine which is providing me the identity is also the machine which is providing me the state of the code running on top of that. And the two are not isolated. Otherwise, it will be no useful, not much of any use, meaning I could provide the state of a different machine which is running a correct software, and I could map it to this machine on which I am running a malicious software. So that will break all the guarantees. And how we think more formally about it is that binding evidence to TLS session, as was also proposed in the BOF, like what it means is that every evidence that is generated, I can use it in that specific session and no other session, which is a very strong guarantee that even if the server was malicious, it couldn't use it in any possible other session, even with the same client and even with the other clients. And second one is that evidence is generated by the same server that is authenticated, somehow related to the above one, that the two guarantees are not coming from different machines, they are coming from the same server. Here is the diagram which explains the changes with respect to the code, with respect to the standard TLS. And there are quite a few details I will try to explain, meaning that, so on the top, the two entities, the first one is saying what TLS role it takes, that is server and the client, server on the right and client on the left. And the server, and on below that, there is the remote attestation role, meaning that who is the attester and who is the verifying relying party. So I have the case of server as attester, which is a very typical case in confidential computing, which was also the use case mentioned in the internet draft. And below that, there is the initial knowledge. What keys do they know initially at the start of the protocol? In this case, they know the ephemeral key, the attestation key. The server knows, the ephemeral key and the attestation key, and the client knows the public part of the attestation key. It has been provisioned, like kind of following the triangle that I showed before. And now, what are the changes with respect to the TLS protocol? And this probably will answer Jonathan's question, which is that the hash of the public key, pub EK, is put inside the R data, the user data field, which is a custom field where one can put any desired data in, even in addition to this public key. And then the signed data means that the client hello nonce that the client, the nonce, the attestation nonce that the client sent in addition to the typical TLS nonce, is added in addition to our data and to the device state, device status. Device status here meaning all the attestation claims that it collected. And from that, the evidence will be generated by signing it with the private key of attestation key, private part of the attestation key, or all that signed data, and then certificate will be self-generated using a private key, which is the priv EK. And it will be signing the pub EK and additionally the evidence that it just generated. With that, it will then provide proof of possession of the ephemeral key in the SIG variable, and that will then sign the log up to the certificate so that both can match on that. And on the client side, it will check the freshness meaning the freshness of the attestation. It will verify the signatures over the evidence which is created in the using the public key, public pub AK. It has already the authentic public part of the key, and then it compared the hashes, like all the piece of code which was running, that all reference values. That was one of the assumptions provided by the system, that assuming the reference values are correct. So the other thing is that it will then client will finally verify with the public key the log CRT, which is the log up to the certificate that both have agreed upon, both have seen the same transcript. So these are the changes with respect to that. And if we already see the protocol diagram, we see that long-term key is not appearing anywhere, which means that it will break already the server authentication property. And not only that, the Internet Architecture Board strongly recommends not using, and actually not recommends, it actually prohibits the use of attestation alone without authentication, and that's where the problem is. Yes, please.
So if I got you correctly, the slide shows the delta between TLS and attested TLS?
I would say delta between standard TLS and the proposal that the authors made for this specific draft for confidential computing use case.
So presumably the long-term key is still being used, right? Because it's the standard TLS key.
No, so they modified TLS and that's not being used.
So
So they
because it
modified
seems
that,
like I mean, how do you have any idea of why that happened? Because it seems to me like not an easy thing to miss if you change the spec and and you remove usage of the long-term key, or did it just accidentally happen?
No, it's not by accident. The idea is that instead of providing the identity in the certificate message, they wanted to carry over the evidence.
Okay, that would then suggest that the authors didn't even intend to bind to the long-term key. Is that correct? Because if they say, oh, well, actually, we don't want to care about the long-term key, we want to care about something else, I guess then it's fine to throw away the long-term key.
One of the authors was just here. He just moved out. So he would have been nice to have him have his opinion. So anyway, in my understanding, basically, the idea was, and that's one of the things that I will talk about in the threat model, that realistic. So what they say is that we don't care about the machine which is carrying the, on which the code is running. And we believe that is actually wrong, meaning that if you don't know which machine you are running, it could be mapped to some other machine which you do not want to connect to, which I will show in a couple of slides, like the real problem with this specific solution.
Okay, thanks. I'm looking forward.
Yeah. Okay, so who is next?
So just to understand, this is not your final proposal of we're going to do. This is something you're going to say is broken.
So just to be clear, so are you asking this is not our final proposal? Is this correct?
Yes.
Yes.
Yeah.
So this is the older draft. Sure. So this is the older draft. I'm just explaining what they did and how did we reach the new proposal that we have. So the new proposal will come afterwards. So this is just still the history of where we started or where the authors actually started, how I got into this verification, and then why we think it's bad and why it breaks the IAB rulings, and why we need to have, for instance, like some other solution like post handshake. So that solution will be in one of the slides or a few of the slides. Okay, with that, this is maybe going to answer the question of why this is bad and why identity is essential, meaning that if we only send in the certificate message, only the evidence that is about the state, and the client wanted to connect to, let's say, cloud.example.com, what would happen is that, or what could happen is that it could be rerouted to any other machine anywhere in the world because nothing is being checked. No identity check is there in the whole protocol that I showed. Long-term key was not appearing anywhere. And it only checks the measurement of the piece of code. I know that, okay, maybe it's not being compromised, but there is no guarantee, which drastically increases the scope of the problem to trusting that each and every machine in the whole world is uncompromised, rather than saying that only one specific machine for which the identity I check, the identity of that specific machine that I'm running on is compromised. So that's what we believe is a real problem, because you are drastically increasing the state, the attack surface for the end attacker. And confidential computing by itself is not bulletproof. Like it could be, there are several attacks already known, which one can utilize in order to, let's say I can break one machine in the lab and then I can reroute the connections to myself, my laptop, and then I can reuse that to, I can use that machine to actually break the security of everyone, theoretically. Right, so the solution we propose is both have to be combined. The two chains I showed have to be combined, and the way to do it is that, and the rationale for that is that CA provides you the identity, the hardware manufacturer or the attestation side provides you what's code, and hardware and software firmware is running on top of that. Both are complementary, can be combined. Certificate verify message of TLS is not extensible, and the proposed solutions which we proposed to the authors were namely 5 solutions in the intra handshake, which their draft was. First one being that I can modify the certificate verify message itself to provide proof of possession of 2 keys, one identity, one attestation key. And then the second one was that we can use multiple certificate verify messages, keeping the structure the same, One provides for one key, the other for other key. Third one was a channel binder, which required changes in the TLS protocol itself, meaning that remote attestation layer bound to the TLS session such that the two cannot be misbinded. And then adding a new attestation message within the TLS protocol, again, a big change. And finally, from cryptographic perspective, adding new signature schemes, which do not change the TLS protocol itself, but somehow provide the both keys or link somehow two keys cryptographically. And then from here, we saw that actually, like Chris Patton, actually, thanks to him, he proposed that, hey, there is a very simple solution for this, and why don't you explore this? And that is namely on the right side, post-handshake attestation based on RFC 9261. And I show here like server as a tester, specifically because client as a tester is already supported by TLS, which is namely the section 426 and 462 of RFC 8446, which already provides the functionality for the client as an attester, but it's not biosymmetric, which means that I cannot do server as an attester with that. The main idea here is that I establish a typical TLS protocol with the TLS protocol, the one-way authenticated channel. And then on top of that, I send two messages, namely authenticator request and authenticator. Authenticator request is this client certificate request message. And the server will then generate authenticator with three messages: certificate, certificate verify, and finish. They have the same structure as the original messages in the TLS. I will describe now a bit of details of this. And this is, by the way, our now current proposed solution, or the initial solution which we have now. And we believe it's much better than changing everything in the TLS and protocol, keeping TLS as it is, and just binding it to the underlying TLS session using exporters as defined in RFC 9261. So a quick overview of what RFC 9261 says. As I said, there is an authenticator request message after the TLS one-way authenticated channel has been established. And that is basically very similar to the certificate request message in the RFC 8446, exactly the same structure. And the authenticator keys are generated via the exporters from the TLS session. With that, how we use it in our own remote attestation protocol solution is namely that we do not change the TLS protocol at all, and we set TLS server as the RATS attester. I need to send a nonce in addition to, not in addition, I mean, in the certificate request, client certificate request, I will send over a nonce, and the server will then put the evidence in addition to the X509 certificate, in addition, as an extension to that message in the evidence. So the protocol diagram is like this, and I only show the post-handshake flow, which is, I will start with, or namely the client will start with sending over a client certificate request with the certificate request context. Server will then generate an evidence, and it will use this context in addition to the exporter coming to that, and that exporter will basically bind it to that specific session such that the evidence cannot be used in any other session. So that is the purpose of that. That meets the property of evidence bound to a TLS session and unique to a specific session. And then certificate message will be extended by certificate for a long-term key plus the evidence. And the other things are as it is, like the other two messages are just as in RFC 9261. The step that will be added at the client side will be that the evidence will be appraised in addition to checking the identity of the server. So we went over to the realistic threat model, whether that is what the confidential computing folks claim. Is it really realistic or not? Coming back to remote attestation only. And what we found is that in all public cloud cases, the cloud service provider is actually trusted for the availability, meaning that if it does not give response to what we have asked for, you cannot do actually anything. And secondly, for machine identifier, that is the identity of that server, let's say server as the attester, and it really violates the host affinity requirement of data sovereignty regulations, and there are several of them, these regulations now, and also the location, because the cloud service provider is the only entity which can provide that location. There is nothing to be attested. It's just self-attestation. We cannot, there is no real check of where that machine actually lies other than the CSP itself. And this also violates the location affinity requirement of data residency regulations. In addition to that, more technically, the CSP is trusted for any part of the boot software that is not open source. So if the code is not open source, how can I compute the reference values? I have to somehow trust them that the values they are giving me are correct. So it's like still trusting the CSP to say that, hey, this is the actual hash value that you should look for. If I don't have any means to reproduce that, or even I don't have the open source code, I have no guarantees on what that piece of code actually does. And then there are early boot measurements, which are when the machine boots up. These measurements, if I am at the real early stage, I don't know what is measured, then all bets are off at that specific point, and we still have to trust the CSP for that. And even in remote attestation, the cloud service providers play a major role, keeping them within the TCB, the trusted computing base. So I have here a table for the three major cloud providers, meaning that you see crosses in each one of them not meeting these requirements. And in summary, like you still have to trust them in order to run your workloads on the clouds. As an example, Microsoft Azure has this structure, which is the confidential VM. And the measurements are done in two separate stages. First, done by the hardware, which you see at the bottom, measured by SEV, SNP hardware, which is by AMD. And on top, some measurements done by the virtual trusted platform module, the VTPM. And combining both, you can have the guarantee that what is running on top of that. But the point here is that other than the things that I mentioned on last slide, it's unclear who owns the seed for the endorsement key of VTPM, which is really important. The one who owns this key is actually trusted. So if it's still Microsoft who owns this key, even with all of the ones which I had in the last slide, even if everything there is resolved, even if there were all ticks there, with this key, they still remain in the TCB. And then finally, who signs the endorsement key for the VTPM? Because the VTPM, as you see, it's going to measure the upper layers. So if that key is signed by Microsoft itself, it remains within the TCB, and all the measurements which the VTPM does will still be controlled by Microsoft itself. So the summary being that you still have to trust Microsoft, and it's unrealistic to say that the cloud providers are out of the TCB. With that, I will conclude that, as I said, the threat model claimed by the Confidential Computing Consortium, meaning that the cloud service provider is out of the TCB, is trivially broken, as in the last 3-4 slides I mentioned. And from our understanding, post-handshake attestation is a more suitable candidate for use cases requiring runtime posture assessment, because for other two solutions, you really have to either break the connection and reconnect again, or do some other technical mechanisms which will be really complicated, and likely this is going to be a better solution and a clean one with still the binding to the TLS session, maintaining all the guarantees and doing it in a better way. There are several corner cases, as I have shown in different slides, hence formal analysis is required. There are huge usability barriers in the tools that still need to be resolved, and we are working towards the formal modeling of the post-handshake proposal that I showed, that once you build the connection, and finally We are also trying toward making Proverif more accessible to the designers. Designers here meaning the ones who are actually writing the specifications. Felix.
Okay, you were done, right? I wanted to make.
I think so. Okay, so yeah, these are the references, and that's pretty much it.
So, yeah, thanks for the presentation. I have two questions. One is rather technical. So initially you presented the goals of integrity and freshness. And I have thought a bit about this. I don't really understand what...
Are you referring to the security, this one, right?
Yeah, exactly.
Yeah.
I don't really understand what freshness is, I think. So I'll just give you it. To me, both of them seem like an authentication property, right? If I'm running as a verifier, the attestation protocol, I want to know that if I believe the machine on the other end is in some state, then it actually is in some state. And freshness means it has not advanced to a drastically different state, I presume.
Before you continue, let me correct that exact point. So the authentication has nothing to do with the state of the device. Actually, state is related to attestation. Authentication only provides you guarantee of the identity of the machine, like it's the TLS.
Well, I didn't want to use authentication in your terminology. I wanted to use it as like, it seems to me like you're going for some sort of general authentication type property.
Right. I mean, it's not our terminology. The RFC 8446 also uses authentication in this sense. And also the RATS RFC 9334 uses attestation in the same sense.
I just wanted to say I didn't intend to use authentication in a formal way. Like not appealing to some specific definition of authentication in a specific document. Just but both of them go in like an authentication direction, right? Where you have, if I believe something, then I want this to correspond to the actual state of the world.
Not really. I mean, one has to do with the authentication has to do with the identity, like the subject alternative name, the fully qualified domain name or IP address or things like that.
I mean, you can authenticate all kinds of things. You can.
Can I just jump in?
Jump in, yeah.
So, one of my favorite papers is called A Hierarchy of Authentication. And it sort of defines lots of different things you could mean by authentication. And the freshness claim is what that paper would call injective authentication. So there's a one-to-one mapping between if the client thinks it's run the protocol with the server once, then the server thinks it's run the protocol with the client once. So the freshness doesn't mean, oh, it hasn't advanced to some drastically different state. It means the server thinks they're running the protocol the same number of times as I think they're running the protocol. And the integrity is what would be called a strong authentication property, which is we agree on each other's identities and on some DS, some extra data. And so they are both types of authentication property, but they're not the same authentication property, and you can have one without the other.
Okay, cool. Yeah, thanks. I mean, Usama, if you agree, that answers my question.
Okay, sure. So yeah, I mean, it's not the terminology that we use in RATS. RATS will be very unhappy with this. But of course, like from Lowe's hierarchies perspective, I would say, yeah, its integrity is non-injective property and freshness is injective property. But the way we are using it is the claims are related to attestation. So in that sense, basically, we are referring to that. We are still modeling it as a non-injective and injective properties, but not necessarily calling them as authentication because it really conflicts with the terminology in RATS. But yeah.
Okay, and then the second question on this overall storyline. So you said there was, on a very, very, very high level, there was draft 1. It didn't do what you think it should. There was draft 2. It does what you think it should, right?
Sorry, so again, so you are talking about this one, right?
I'm talking about your entire presentation, not necessarily a slide.
I mean, because there were 2 drafts, so which one are you talking about?
Yeah, exactly. I want to get to the delta of the 2.
Okay.
So I don't think they're not different versions of the same file name. They're different drafts entirely.
So one is intra handshake and the other one is post handshake.
Yeah, previously you showed us a slide with a protocol diagram. You said this didn't provide the security guarantees we wanted. At the end, you showed us a new protocol diagram. You said this does provide us the security guarantees we wanted.
No. We don't, for the new one, we don't claim anything. So we haven't verified that yet.
Okay, you
So
think it will
We
provide the
believe
guarantees you wanted.
hopefully it
Yes.
will provide some good properties, but we don't really know.
And you said the problem.
So this one is the older one.
Yeah.
This is what we have formally analyzed
Yes.
and not the next one.
Yeah. And you said the problem was the TLS long-term key that got thrown out, right?
Right.
So is it accurate to say that this draft degraded the security of TLS?
Yes,
Yeah.
I would say so.
So basically you could just ignore the server certificate because the key's not there.
Not necessarily ignore it, because they still have the certificate message,
Yeah.
but the content they put inside the certificate message is different. Rather than putting the PKI certificate, you put it an evidence like the cert message that you see here.
Yeah. Okay. Yeah. But the standard web PKI TLS certificate that you don't see at all.
Yeah, PKI certificate is not there.
Okay.
Yeah.
Cool. Thank you.
Yeah, welcome.
Jonathan?
Okay, who's next?
So if you could go back to the slide you were showing Felix quickly.
Which slide?
The slide which said integrity, freshness, this one. Yeah.
This one.
So this is something that's actually very, I wrote about this in my thesis a million years ago. This is actually something that is a bit subtle and weird in exported authenticators. So with exported authenticators, you know that the signer of the exported authenticator shares state with the signer of the TLS session. And if you send two exported authenticators, you know the same thing. You know the signer of the EAA shares some state with the signer of the TLS session. But you don't get a guarantee that the signer of the EA1 is also the signer of the EA2, shares state, sorry, with the signer of EA2. And so your refresh doesn't prove that you're talking to the same TEE necessarily.
So I think that so my understanding here is this one, that I don't necessarily need to bind EA1 and EA2, because what was the state of the machine yesterday would not mean a lot to me what I'm checking right now. And I still need to ensure that I am still talking to the same machine. I mean, the certificate message here, which is post handshake in each authenticator, that will still bind to the same session. And since I know from the standard TLS that I connected to that specific trusted execution environment, I would still have the guarantee that it is still the same TEE. My understanding is that both authenticators, exported authenticators, one today and one yesterday, if I requested two authenticators, they don't need to be linked together.
So if you think of, we're out of time, but if you think of, let's say I've got my VM running and I then fork my VM. My VM's running, I do a TLS connection, then I fork my VM. And so now they both could write to the session. It's contrived, but imagine you forked your VM into two different VMs, both with the same state.
So they can have the same state, but they would have different keys, right? So they would differ with the keys.
Well, not if you forked it. That's my point.
Okay.
But anyway, let's just, just as a example, the left one could create an EA and send it. The right one could create an EA and send it, but they wouldn't be from the same session, even though, because you forked your TLS session. I mean, the more common case is obviously proxies, right? I have a TLS terminating proxy, and it just sends the exporter key to some backend, which signs it and sends it back. And so that's the case where you really see this as a problem.
Right. I believe there are a lot of assumptions here which might not be realistic. Number one being that you have the same exact long-term key, you have exactly same attestation key, you have exactly same session keys, or otherwise they are leaked in that, or they are forked together, everything together, or it's a complete clone of that. And it's still, if all of these three are lost, then of course, like the guarantees are off. But I believe really this is maybe a hypothetical case and not realistic in our
I mean,
understanding, at
it
least.
might not be realistic for your scenario if we're assuming that there is no TLS termination. But in TLS land, TLS termination is quite common. Should we move on to the next presentation?
Right. Thank you very much.
Great. Thanks, Osama. And there was a BOF about that. I posted a link in the chat to the details for people who are interested. I guess the follow-up on that, Osama, is on the expat list, right? Or the follow-up to this is on the expat list. Okay. So Tahini, I assume you want control the clicker?
Yes.
Thank you.
Yes, thank you.
So far ahead,
Hi,
you've got about
can you
an
hear
hour.
me? Oh, no. Oops. raté. Hi, can you hear me? Thank you.
So thanks for coming on. So this is some work we haven't seen before, and should be quite interesting. Would you like people to jump up and down as you go, or would
Yes,
you...
I believe it is better that people ask questions in the middle. Please interrupt me with questions. Yes.
Great, thank you. And off you go.
Hi, I'm Tahina from Microsoft Research, Tahina Ronanandro. I'm based in Redmond, next to Seattle in the US. And I will be telling you about EverParse, which is a research project that has been ongoing since I joined Microsoft in 2016, about verified parsing and serialization for binary data formats and making it accessible to everyone. So as you all know, I believe secure binary data parsing is one of the major root causes of software security vulnerabilities. And most of such vulnerabilities are due to handwritten parsing code, which is especially disastrous in memory unsafe languages. But even if you switch to Rust, that alone will not remove such vulnerabilities about runtime panics, functional bugs, and even some security properties that I'm going to tell you about in the next slides. Because writing such a functionally correct parsers is indeed hard in terms of endianness, data dependency, size constraints, and others. And even as recently as during the pandemic, some more bugs were found even in the TCP parser, packet parser in the Linux kernel, or also in Windows, in the Windows networking stack. So what we advocate here is to first identify families of security critical data formats and design format specification languages to support them. And then given a family, we implement an once and for all probably correct low-level code generator that takes data descriptions in such a format specification language and generates parsers, serializers, and so on in C, Rust, and WASM with formal guarantees. And then once we have this code generator available, we can give them to the user so that they can provide the data format specifications and just push a button and so they get a generated code with all such formal guarantees without doing any proof of themselves. So zero user proof effort. And then once they have this code with such formal guarantees, they can replace their existing code with within larger applications, either unverified or even in larger verified code. So in this talk, I'll give you one representative example of deployment of EverParse that we have had at Microsoft, especially in Hyper-V for network virtualization. But there have been many other cases, such as ELF for eBPF, ASN1, CBOR and CDDL, TLS, Quick, and others. So EverParse has been a wide collaboration between Microsoft Research and Microsoft product groups, and also some external contributors and former interns. I can see a few of them here in the room. Dragana, thank you. And EverParse itself is one component of a larger research project that happened before the pandemic, which is called Project Everest. Its initial goal was to prove the correctness of components in the HTTPS ecosystem, including the TLS 1.3 handshake. And overall, Project Everest has amounted to around 1 million lines of F-star code, where F-star is the, oops, is it the right deck? Yes, the F-star language that is our proof assistant and dependently typed programming language. And I'll show you a few examples on the next slide. This Project Everest has covered cryptography and verified parsers and has been deployed in Linux, Firefox, Python, Windows, Azure, and so on. Even though Everest itself has been considered over, the offspring of it, that is EverParse, EverCrypt, and other sub-projects that have grown as independent projects of their own, have been continuously active standalone projects. So today I'm going to tell you about EverParse. I could have told you a bit about EverCrypt, but the call was explicitly about non-crypto uses of formal methods, so I won't tell you anything about those. So what is our methodology with F-star is that we write our implementation is in a subset of F-star that extracts to C, WASM, or Rust, while using the full power of F-star to do the proofs. And so when we extract such subset, we get efficient implementation code in the sense that verification imposes no runtime performance overhead, because everything will have been proven ahead of time, at compile time. In fact, in our most recent work in EverParse, we have been using separation logic to prove the correctness of our code that we also presented last month in June at PLDI. So what do we want? We want users to just write a data format description in some data format description language that they extract from external sources of truth, such as RFCs or anything. And then they push a button and we automatically do the rest. That is, we produce a formal specification in F-star along with the verified implementation against that formal specification, proven correct for memory safety, arithmetic safety, functional correctness, and other security properties that I will tell you about in the next slide, such as double fetch freedom and so on. And then we generate a C code that we then integrate by replacing existing parsers in such applications as Windows and Azure Hyper-V network virtualization. So what formal guarantees do we mean? So memory safety, that is no buffer overrun, no out of bound buffer accesses. Arithmetic safety, no integer overflow or underflow or anything. Functional correctness in the sense that we reject all ill-formed packets and we accept all valid ones. Some security properties we may be interested in depend on the application. For such contexts as TLS, ASL1DER, or CBOR, deterministic subset, COSI, CDDL, and so on, we want non-ambiguity and non-malleability in such a way that serialization parses back to the same value that you wanted, and that you have a unique binary representation for hash-based authentication. For other applications, such as Hyper-V at Microsoft, we want to ensure that we can validate input buffers where we don't have ownership of. We don't have exclusive read access, and so we need to make sure that we read each byte at most once. And so we actually perform validation on somehow a logical snapshot of the input data, which allows us to defend against bugs such as time of check versus time of use. Yes?
Yeah, hi. You so quickly said unique binary representation for hash-based authentication. Could you elaborate what that means?
Alors, there has been a bug in, say, early implementations of Bitcoin blockchain, where an attacker crafted one representation of a binary transaction and inserted it into the blockchain, and then crafted another representation of the same transaction and then hashed it and then presented the hash and said, oh, actually the hash mismatch does not match the one that is in the blockchain, and so I can claim that the transaction did not happen. So this kind of authentication bug has happened earlier in early implementations of Bitcoin blockchain in 2006, I believe, and that's what we are defending against.
And the problematic part is someone being able to enter something that is ill-formed, right?
Yes, not necessarily, sorry. That is, if the form, it's a security property of the format. That is, if the format, if the user uses a format that is not deterministic, then they can produce several binary representations, produce different hashes for all of them, and then they present one to one party and another one to another party, and then they can claim whatever they want about, oh yes, this happened, this did not happen, and so on.
Okay, thanks.
Sorry, thank you. Okay. Yes, and then we defend against, in other applications, we defend against time of check versus time of use bugs using, with double fetch freedom. Okay. So, John, just quickly about our specific application on Hyper-V network virtualization. So Hyper-V is the hypervisor for Windows 10, Windows 11, and all Azure Cloud, where actually Azure VMs are running on top of hosts that run Hyper-V to coordinate them and so on. And within Hyper-V, there is a component called vSwitch, which is the network virtualizer, which dispatches network packets from and to guests, from the network to the guest, and conversely. In general, when you do such a network virtualization, you should use hypercores, but sometimes you believe that such hypercores are expensive and you want some optimized direct hardware access that we call VM bus. And so when we do that, we expose some attack surface to malicious guests because we potentially break isolation. And so we need to protect against such attackers that could craft ill-formed packets to break isolation or gain host access. And that's where we introduced, or Everparse produced verified packet validators that are now running such a way that every network packet that goes in or out of Azure is validated by Everparse formerly verified code, and that's what I believe is the result of having applied a usable formal method. That's why actually I'm giving this talk here. Is that I'm showing that yes, you can provide formal methods techniques that can be used by users with minimal or zero proof effort in that case, and that can have a huge impact in real world. And in fact, so it is about checking that all the virtualization layers that are added to the network packet to help the hypervisor dispatch to the right guest, to make sure that all of those layers are parsed correctly. And you can read our Microsoft blog post. Verification time is tractable, less than 2 minutes, and it generates 30,000 lines of C code. Yes. Okay, so how do we do that in practice? So first, we need to extract some data format descriptions and write them in some data format description language. So to do that, we defined such a language, which we call 3D for dependent data descriptions. So here we take some C-type definition for TCP header packets, TCP packet header, sorry. And 3D augments such a definition with value constraints, so constraints on scalar field values, variable length structures, that is how to determine the length of some, the byte length of some arrays or anything. Value-dependent unions, that is to choose the right case of a union depending on some value that you parsed or computed before. And parsing actions, so that you can read some of the data that you parse and write it into some out parameter. And this gives you full control about what you want to read, while basically you can check the constraints at the control level, and then you read through actions from the data level. And then once once the user writes a data format description in this 3D language, then they push a button, and we produce F-star code for the specification and for the implementation that we then extract automatically to C code that is readable in such a way that it has readable variable names and preserves comments from the specification so that the generated C code can be auditable. Alors, some of you here or online may have been at the side meeting on Tuesday about CDDL and may have seen that the code was probably less readable for EverCDDL than it has been here for EverPath 3D, but one of the reasons is that the types generated by EverCDDL are more complex than those for 3D, and there are fewer opportunities for CDDL description authors to insert names to name their types for alternations or anything. But we plan in the short term to improve that situation on CDDL as well. We know how to do it for 3D, and so we are confident we can also extend that to CDDL. And then we replace the existing code with our automatically verified generated parsers, where we managed to meet performance bars that is less than 2% overhead as mandated by the product teams. Even in some cases, we are even faster than the original code because we avoided some copies because of the double fetch freedom guarantee that we offer. That is, we don't need to copy the input buffer since we can guarantee that we read each byte at most once. And the productivity improvements in the whole pipeline is critical to meet a product deadline as stated by the product team, the engineering lead of the time, Omar Cardona. And since then, product teams have been able to autonomously update the data format specification and push the EverParse button without us without the research side intervening in any way. And so this has allowed EverParse to propagate within Microsoft to 3 other areas of Windows networking that I cannot give more details about at this time, but also in other components such as the eBPF for Windows.
You have a question?
Yeah, Stéphane Bartsmeyer, AFNIC. My question is in 2 parts. To take the example of TCP parsing, what do you do with the option? I mean, do you check every option or just that they fit the general rule for an option? And then I have another question, depending on your answer.
I don't have the details to that question, but I believe that...
okay, my point was, yes. If you don't, if you just check that any option is option type, etc., yes. Then you may miss some parsing errors, parsing of the options themselves. But if you do check, there is a risk of ossification, which means that new options will have difficulties to be deployed.
Yes.
And with every protocol with options like TCP yes. or IPv6 with the extended headers, there is always this tussle between checking everything for security on
exactly.
Avoiding ossification of the network.
Alors, we have, actually, that's exactly the question I'm asking at the very end of my talk, is that how to interpret that RFC 1122. But we tend to favor the latter part, the latter of your that is to determine a fixed set of options so that then we can extend it later. That's what I was mentioning by the product teams can autonomously update the specification to support more options as time goes.
Okay.
Good.
I had a you produce at the end of the run, you produce formally verified C code.
Yes.
And I was just wondering, is that what kind of model of C you are using to verify that code?
Alors, we have a model of C with arrays and unions and structs. Okay, so right now it is the compilation itself is not formally verified. We could use something like compcert to do that. I mean, there are verified compilers. Sorry, the extraction from F* to C is not verified yet. We have a paper proof in the ICFP 2017 paper. There have been efforts to verify that ongoing. But yes, basically it's a model of C that currently does not support things like field pointers, but we plan to add them in the near future, especially since we switched to separation logic.
Okay, so you're generating first F* code and you're verifying that and then doing the extraction.
Yes.
Check.
You have another question?
Yeah.
Yaron, Chef, a very high level, possibly silly question. Mm-hmm. So the first stage of the conversion from for example, the RFC that defines CBOR, that's manual.
Yes.
And that is not formally verified because there's nothing to formally verify against. Correct?
Yes, that is the trust in the specification. You still need to review the specification, and in fact, that's what I'm going to tell you a little bit about in the next few slides. But yes, at least what we mean is that it is easier to review specification than to review code, and that's why we lift the review problem to the highest level possible, and then the rest, once we have a formal specification that we adequately reviewed, we can generate code in a verified way with respect to that specification.
Okay, so what is formally verified is the later stages of the conversion,
yes,
as well as some specific security guarantees.
Yes. Yes.
Okay, thank you.
Voilà. And sorry, 1 second. Yes, okay. Yes, we were saying that the product teams at Microsoft were really happy with what we have, and that others have been adopting it internally, at least. Yes.
I really would like to answer the question that Yaron did not ask. Of course, in the long run, we want to have formal definitions in the standards.
Exactly, yes.
So I would expect that problem, which clearly everybody has in mind when they look at this, can be addressed. It probably would be good to actually have more than one formal specification at the point in time when we do that.
Ah.
But yeah, having a formal definition in a specification would be the thing that I think should be the ultimate outcome of this research.
Ah, that's interesting to have more than one formal specification. That's interesting.
Carsten, if I may ask a follow-up question, what's the benefit of having a formal specification in the draft versus in some repository?
Alors, I believe I can answer part of it. I can answer part of it is that to have a formal specification that is amenable to automatic processing for such code generation tools that can produce parsers and serializers. That's actually what I want. Yes, it's part of my conclusion of this talk is that ideally we should have standards that define such formal specifications amenable to formalization in proof assistance, and then to automatic code generation, verified or not, but already to yes. And then maybe Carsten has a more a precise answer.
I have a very different answer, which is since 1977, we have ABNF in our documents.
Mm-hmm.
All those text-based protocols have ABNF definitions if they're good. That turned out to be human-to-human communication, and it was useful. Then, like 20 years ago, we started to have tools that actually generated code from these ABNF definitions,
Mm-hmm.
and we found a few bugs. Yeah, now the ABNF definitions are better, and at least in certain working groups, we don't do things without actually building code from the ABNF definitions. Yeah, I'd like to have the same situation with things that cannot be easily done in ABNF,
Yes.
and with things that actually need a transformation and not just a validation function for that formal specification.
Yes, thank you.
About Stefan Bartsmeyer again, about this issue of formal specification in draft on RFC.
Mm-hmm.
Today, we already have a lot of formal specifications, such as
Yes.
ABNF, but not only. The problem is that there is also natural language text, and they don't always agree. 2 days ago, in the regex working group, for instance, there was a huge discussion about a bug which was reported against one of our RFC, because the formal specification on the free text disagreed, and it was not catched in the normal working group process.
Yes.
So maybe the future will be a RFC entirely written in the formal language, but.
So I suggest we kind of try and speed up a little to let him get through his slides, and then have this discussion then. So.
Yeah, I'd like to make one quick comment on this. Documents that have English language and formal specification in them often feel a need to actually say one has precedence over the other.
Yes.
And that's wrong. And this is one of the jobs of this research group, to find out how to handle this right. Because any discrepancy between the English and the formal specification is an errata. And you have to treat this as an errata and not as a situation where one has precedence over the other.
Okay.
Yes, and there has been some that we discussed 2 days ago at the side meeting about COSI, for instance, where there is a text for COSI, the text normative natural language text for COSI, and CDDL specifications for the same, and those CDDL were considered not normative, and they are wrong in terms of, they introduce discrepancies, and so it's not amenable to automatic processing, and that's what we hope to change.
So one last word about this, and please don't take it as a joke. I think AI actually can serve a part in the top level of comparing English specifications to formal specifications where they exist, or more likely where they don't exist.
Yes, that's my next slide. Thank you. Thanks a lot. In the sense that, yes, if we don't want to spend that much effort in building domain expertise to manually write a specification and so on, we can try to use AI as you were proposing. And that's what we have done. We have an ICSI paper accepted that we presented at ICSI this year about generating data format descriptions from the text of the RFCs, generating such a data format descriptions in the 3D language, and then more precisely, we do not just generate that and accept it, but we use the data from the generated specification to generate test cases, and then to run such test cases with the legacy parsers and to check whether the intent is indeed so the specification is indeed matching the intent, especially as by legacy parsers. And of course, this approach carries the problem that if the legacy parsers are buggy, then we tend to backport such bugs into the specification by the feedback loop. And that's why we mean that human review is still necessary for such specifications, but at least symbolic methods, such as automatic test case generation, are still useful in making that review burden lighter for humans. That's why I mean we should not totally rely on AI, but we can use symbolic non-AI methods to help us perform such reviews. Okay, so this is how we implement the AI agent to generate such specifications. It's basically a planner agent, a 3D agent, and a domain expert agent that have specific prompts so that the LLM behind can be asked, can be tasked with a very specific task so that it does not have too much context, or that is the more precise the task, the more accurate the outcome, and basically it was just a matter of writing the right precise prompts for each agent, and then having such agents communicate with each other. And then we had we tested such methodology on many internal protocols, IETF and so on. But those are results from I think April of this year. Yes, please email me and my co-authors for more details about those. They can answer better than I can. But it's basically yes, what I was meaning that. We can use the symbolic methods to help reviews, but...
I have a question on the previous slide.
Sorry.
So can you... A lot of these are relatively low-level protocols. Which of these is the most complex to deal with? And how would that compare to something like HTTP or email?
Let me think. Okay, so we can just mean by the sheer number of pages, I would say DCCP, but it may not be the most complex in terms of intricacies, but I would say, what was the result? I have to ask my co-authors because I think they have a better answer to that question.
Okay.
Yes, because I'm more on the symbolic side than on the AI side, but I'm just saying that the two should go hand in hand. And yes, that we can use symbolic methods to alleviate the review burden on the human, but we still need to perform such human reviews. We won't eliminate that completely.
David?
Yes. Oops.
Oh, okay.
And then the next step is to do the integration also automatically by asking AI agent to identify the parsing logic from existing code, and then refactor the code base, and then to use the isolated parser as an input to 3D gen, that is the specification inference that I just presented. And then to replace that isolated parser with the parser generated by Everparse. And this is work in progress. And so this would have automated most, if not all, of the pipeline with a combination of AI and automatic verification. Voilà, and then yes, well, that's what actually you anticipated on my conclusions, is that yes, we should have formal data description languages in RFCs, and probably we should hopefully have them take as much precedence as possible. Alors, I know that there are many such examples. So, for instance, we have the TLS handshake that uses one format, and then we have CDD, one format description language that we have a code generator for. That's what Usenik Security 2019. And then we have CDDL, and then we have 3D, and so on. And then voilà. So that's why if there is any way to summarize at some point the data format description languages that are present in RFCs, so that we can assess their use, assess their definitions, and strengthen the existing RFCs also in terms of adequacy between the data format description and the normative text. And then you also mentioned previously that should we revisit Postel's principle in a security setting? I believe that we should be as paranoid as possible about what we receive to avoid such attacks, in the sense that I believe, for instance, that it may be harmful to start advancing some state depending on parts of a packet that we read until we identify some point where actually the rest of the data is corrupt or ill-formed. And too bad, we already advanced the state. I hope we can avoid that and do something like pre-validation, and that's what we are advocating. Yes?
Do you want to just finish, go to your last slide?
And that's pretty much all, because then, yes, it's those are the list of papers that we have had and deployments and so on. So that's, yes.
Great. So, yeah, please join the queue, and we have 20 minutes to chat. So yes. Go ahead.
Thank you.
So a couple of slides ago, you advocated for the use of AI in the writing process of the actual specifications in order to optimize that process. Current large language models are kind of infamous for doing a lot of hallucinating.
Yes.
So you claim that this reduces workload, but I guess this still needs to be validated by a human.
Yes.
How do you evaluate whether this actually saves time versus manually getting someone to write a spec?
In fact, by the set of test cases that we generate, that is, it has happened for some protocols, I don't remember which ones, but that the test cases that we have produced were richer than what was existing. And so that's one benefit, even besides the AI itself. Another benefit, side benefit of this approach is to enrich the test case, enrich the test suite. Sorry.
Okay. So let me formulate the question a little bit in a different way that might be easier to get to answer what I'm trying to get at, which is, you claim that this saves time. Did you conduct experiments with humans in the loop that shows that, or is this basically anecdotal experience from using this?
Right now we have not done user studies to back the time-saving claim per se, but we have observed by ourselves that we have saved a significant amount of time in writing such specifications using, so that's where I would say our first observations from ourselves. It is true that we should generalize that by user studies, you're right.
Jonathan?
So to me, I mean, my experience with AI is relatively limited, but to me it would seem much more natural to give a large language model a format.3D file and have it give me a spec from that than try and get it to formalize natural language English, which is ambiguous.
Yes.
It would be nicer for it to, I'm just going to write my spec in format.3D, and then the AI is going to turn that into a beautifully written spec for me.
Yes, you mean that it would be preferable to have formal description languages, formal data descriptions in RFCs, and then using AI to describe them in natural text. Is that what you mean?
Well, yeah, I mean, the formal language doesn't even have to go into the RFC, right? But if I wanted to create a nice RFC, wouldn't it be easier to say, here is what I exactly want in like some formal language?
Yes.
And just the RFC text is generated by a tool. It plays to the AI strengths, right? Like producing text.
Yes. I wholly agree with you. If we can do that, yes, I believe that that's what we should do. But then, yes, there will still be the same problem as is the text generated indeed matching the intent in the formal model. That may be easier to it may be easier to formalize that in terms of computational linguistics or anything, maybe this way than the other, I believe. But I'm not an expert in that area, so this is maybe just a bit of speculation. Sorry.
Felix?
Yeah, the 3D language seems rather rich, and and you do verify higher level properties like memory safety, these uniqueness properties. But I wonder, can you give us because you showed pointers and mutable data structures, and there are like these actions that you can take. So how can you say anything on the likelihood that people make mistakes in this potentially rich, potentially Turing-complete language, and how complex is the language itself?
Most errors would be in the action. There are two classes of errors. One would be in the data format description itself without actions, already in terms of adequacy with
I'm not thinking about like, someone writes you in 16, but it should have been you in 32. Yeah, like this is a human error, like nothing you can do about that.
Yes.
But the more complex you make your input language to this, like you said, we think specifications are easier to validate than implementations.
Yes.
And I agree, unless your specification language is as complex as the implementation language.
Yes.
So I'm wondering, can you say something on the delta of the complexity between the specification language and the implementation language?
Yes, it is definitely not. That is it is definitely not Turing complete at all. That is the actions language is very limited, and it is mostly limited to filling in our parameters because it is just meant for parsing. That is, there is no intent of implementing state machines in the data format description of the format, at least, and to have them and to advance them in the actions. Also, because this would be incorrect if, for instance, the rest of the data were to be invalid. So no, the actions are not as powerful as no. Actions are mostly limited to out parameter setting.
Okay, thank you.
There are actually, sorry, just to complete my answer, there is a point where we do have a new mechanism that is called probing that allows to call a function to retrieve another input buffer from somewhere else. But that is just used in some pointer-rich data structures where we do not want to formalize so we trust the pointer structure in the we trust the pointer value, the format of the pointer value, because, for instance, it is given by the implementation. That is the function that does the jump is assumed to fail if, for instance, the pointer is ill-formed, and this is outside of the scope of 3D. But then within that scope, we can do we can jump to another input buffer and validate the content of that indirect input buffer. But that's pretty much all. That is, there are ongoing work in trying to give a formal specification to what we can do with those probes. But right now, this is fairly limited.
Carsten, you go ahead.
Yeah, Carsten, I just wanted to make a larger context comment. I met Tahina for the first time this weekend at the hackathon.
Yes.
And I kind of remember the questions that always come up. Why do you want to put formal specifications of stuff in there? And I think the answer we have is to keep you honest. That's really what the formal specification can do. It makes sure that the specification actually is honest. And Tahina essentially gave me a guided tour through all the heaps of dirt we had tried to sweep under the rug. And he found them all and explained how to fix them and so on. So that was really interesting. I mean, SIBO has been out there for 12 years, so it's not things we can immediately fix, at least not all of them. But it was really good to see someone take some useful methodology, look at the whole thing, and come up with comments that were worth looking at.
Thank you, Carsten. And yes, it's nice to meet you and nice to have started working with you. And thank you again for the very warm comments.
So I have a comment / question and a question.
Yes.
I have a pretend question and a real one. So the pretend question is, this seems like really nice in terms of getting rid of a whole class of bugs with memory, buffer overruns and so on. If I remember back to when people were using ASM1 compilers 20 or 30 years ago, they obviously had those problems. So great, we get rid of them. They also caused a problem where specification writers would feel very free to add lots of options because they didn't have to hand code the parser.
Yes.
Could this create a similar kind of issue for specification authors, that they add more options because now it's easy again and safe-ish again?
That's very tempting. Alors, what is the risk in doing that? Once, okay. There are two things. One is have such parsers being automatically generated. That is, we can assume that with ASN1, most parsers of ASN1 have been automatically generated with, say, ASN1C or something. Is that true?
It used to be true. I think it's less true now.
Et voilà, that's the problem. That is, I hope that adoption of code generation tools can be sustained, in the sense that such tools should not be abandoned, because yes, as we use them, there is, you're right, this temptation of, okay, since everything is trustworthy, then I can make my specification as complex as possible, until such time as we revert to handwritten parsers, and I hope we are not going to do that. And that's why I hope with formally verified parsers, we are not going to do that, since having such a formal guarantee behind the parsers I believe should be one more reason not to abandon them once we adopt them.
Go ahead. I have another question, but a different topic.
I think I can answer your question. Yes, definitely.
Okay.
So the arrival of those ABNF tools that we have been using certainly has enabled us to write more complex specifications. But this is really complexity in terms of structure a machine would see, that actually can simplify the whole thing for the human user. So this is difficult to explain. But I think the effect that we are seeing there is not entirely broken, because it can actually help reaching results that are simple on a higher semantic level. And yeah, so most of our documents have some security considerations text or some other text that says, folks, this is not meant to increase complexity of specifications by a factor of 10, but to reduce the effort of reading them by a factor of 10.
Yeah, I mean, I guess the interesting kind of danger here, I suppose, is that you end up with a much better parser for the binary blobs, and that will feed a data structure to the higher level code, which now doesn't know to expect some fields to be filled in certain ways.
Yeah,
and then you get a higher level code bug. But I still, I mean, I think overall this is still great, but it'd be interesting to see how that plays out.
I read all 900 pages of ASN1 in the original GSM specification.
And then
so I also had a
question.
real question.
Yes.
Yeah. So the real question is, are there particular things that you'd have interest in working with this research group on to try and get people to use this, to play with it?
Yes, pretty much. That's what I meant on my last slide. Where is it?
Keep going.
To go to the last slide. That slide, sorry. Yes. To promote the adoption of formal specifications in RFCs with clear definitions for such data format description languages, to gather them, and then to use, for some of them to use our tools, to foster research in developing extensions to other parts or other, so that's pretty much all of the goals that I have in general, and I hope that UFMRG at IETF can help.
Great. So I was hoping you'd get back up given your earlier comments, so go ahead. Go ahead.
Okay. One final question. Your current output is C code.
Yes.
Are there plans to provide support for other languages? Because C is famously not that strict in its types, and there's also in processing what has been parsed, there's reasons to have better type systems there.
Yes, you are exactly. You're right. Rust is definitely one of our targets. We have extended our code generator to Rust recently, November, I believe. It is already the case for CBOR, for instance, that we have a C and Rust code extracted, CBOR and CDDL. We also have a WebAssembly backend, but we have not. The WebAssembly backend has been used in. Sorry, I should not have talked about HackerStar and EverCrypt. But we have not tested them for EverParse yet. So C, Rust, definitely. WASM, highly likely, yes. At the very least, those three.
Okay.
What else do you have in mind?
Well, most of my implementations are in Rust, so that is really nice.
Thank you.
Great. Jonathan, anything before we finish up? I don't think there's any other business, but.
Yeah, no, any other business? We seem to manage to use all our time anyway. But,
yeah, great. So let's just thank our two speakers. So thank you.
Thank you again. Thank you for hosting us. And please email me and my co-authors, or please email me and then I will redirect you to my co-authors if you have any questions. Thank you again.
And please, if you're using this or playing with it, then send mail to the UFMRG list as well, so people get to know about it. Yeah.
Yes, thank you.
Great, thank you. That was very good. Thanks. Okay, folks, I guess that's, unless there's any other business somebody wants to go to the microphone, I think we're free to let you grab a coffee and then wait a short while for the cookies. Thank you. And thanks, Felix, for the notes. I'm sure they're very good when I get to read them.
Yeah, I'm one of the developers.
Okay, cool. Because we are currently trying to use the tool. What for? We want to prove an extension of TLS. This proposed extended key update. We want to add it to the model. We are not really getting along well with the tool. We try to build on the old, there's a TLS model, I think, like 8 years ago. try to build on it. It's very huge, and even very simple things. It's very hard to get hold of it.
So I always have people, I think, interested in